Good morning. Happy Monday. Happy final week of instruction. Today we are going to wrap up Unit 8. All right, let's move over to the PowerPoint. And I'd like to start with this slide. This was the kind of the main takeaway, the technical stuff from Friday's lecture. The definitions and methods of calculation for the gain, phase, and delay margins. Again, to refresh your memory, the gain margin is the amount that the open loop gain can be increased before the closed loop system becomes unstable. And the phase margin is the additional amount of phase lag around the loop before the closed loop system can be unstable. If both of those numbers are positive, then they can both be increased by a certain amount, and therefore the system is currently stable. If either of them are negative, that means that in order to stabilize the system, you'd have to increase by a negative amount. In this case, negative dBs means lower or multiplied by the reciprocal. And so the system is currently unstable. And then the delay margin is a nice, I think it's a nice physical way to tangible thing that you can hold on to, that given a delay margin at a crossover frequency, you can calculate the number of literal seconds in delay around the loop, that if you experience that much delay, then all of a sudden your actuator is doing the exact opposite of what it should be doing in terms of real-time control. Okay, so again, any questions now that your memory might have been jogged a wee bit? Okay, so let's talk about an example problem. So, excuse me. For you wish. For this system, we've got a fixed process with transfer function something like 3100 over s times s plus 10 squared. And the question that I'd like to ask is proportional control good enough? And as a kind of a proxy for that question, if I let the controller just be unity gain, is that good enough to make the system stable? If it's not stable, then it doesn't make sense to talk about steady state performance or transient performance, because you'll never get there because your system's unstable. So I'd like to answer this question. Well, first of all, I want to point out that you have multiple tools to answer this question. And the tool I'm going to use is just the newest tool. It's not the only tool. In particular, Ralph Hurwitz would definitely answer this question for you. And then some. Root locus would also probably answer this question in a probably more roundabout way, but you would get more information along the way. But open loop Bode testing is, like I said, a bit more practical, that you could run this system through a frequency response test and determine its open loop Bode plot and then its gain and phase margins from there. So let's start by determining, do we want the open loop Bode plot or the closed loop Bode plot? What do you think?
Wouldn't the open loop Bode plot be sufficient?
Exactly right. So if we're looking for the gain and phase margins, we need the open loop Bode plot. Even though the question is asking, is this closed loop system stable? And I just want to remind you that even though we're looking for a statement about the closed loop system, we are going to be analyzing the open loop system. Okay, so the open loop transfer function, if C of S is equal to 1, is simply C times P. But P is not in leading ones form. So in order to write it like that, I'm going to factor out 10 times 10. And so we get S over 10 plus 1 squared. So there's a factor of 100 missing. And I'm just going to put that into the numerator by moving the decimal place 2 places. Okay, so now I see 4 ingredients in this transfer function. I see a constant, I see an integrator, and I see 2 real poles that happen to be at the same frequency. So let's go ahead and note where the frequencies are going to be. So let's put, I guess we'll put it up here. Well, let's see here. Let's make this 1,000 radians per second. Let's make this 100, and let's make this 10, and let's make this 1, sorry, 10 to the 0, aka 1, and we'll make this 0.1. Okay, so these are radians per second. Okay. So again, we're going to draw the ingredients individually first, and then we will combine them into the overall magnitude and phase plots. So I guess we also need to determine, well, let's do the constant last. So the integrator is going to be, well, let's make this 0 dBs. And so, yeah, we're going to need minus 20, minus 40. Okay, so if this point is 1 radian per second, comma 0 dBs, that's where the integrator runs through. And so this is going to be the magnitude response of the integrator. And each of the real poles is hanging out at 0 dBs until about 10 radians per second, at which point they both roll off at the same slope. And just to remind ourselves that there are 2 of those. And then the constant. So 31.6 in decibels. I don't expect you to know that straight away, so why don't I just show you what's going on. If I want the dB value of 31.62, it's 30. So this is it's a nice party trick. Is it about 30? A multiple of 30 is actually about 30 dBs. That's I don't know. You can impress your friends. So let's see here. The constant is sitting up here at 10, 20, 30 dBs. Is this all going to kind of run into the title there? I think it already is. Yeah, you know what? I'm going to move, actually, I'm going to move the title. This is tricky, I know. And, well, I guess I can just make it smaller. You guys can all read it now. Haha, perfect. Things that you can't do on a whiteboard. Okay, so right now we are going to combine these 4 ingredients. And so this means that the constant plus the integrator is going to hang out here. Right, so I've moved the integrator line up by 30 dBs, which means where it used to be at 0 dBs, it's now at 30 dBs. That's how I made that jump. And then at 10 radians per second, each of the poles is going to be pulling down by 3 dBs. So if we should have been going through this point, which is 10 dBs up, we'll actually be going through this point, which is 4 dBs up. So we're going to start to round this off. And so now we're going to draw the asymptote starting at this point and then rolling off at 60 dBs per decade. So here's 20, 40, 60. So I need to approach this line, something like that. Okay, so questions on the magnitude plot when the controller is equal to 1. Because now we're going to talk about the phase plot. Okay, so we have an integrator, so there's really no point in drawing the 0 degree line because everything is going to just be hanging out at negative 90. So let's make this minus 270. Let's make this minus 180. And let's make this minus 90 degrees. Okay, so I'm also going to kind of jump straight to the overall phase, particularly because there's only 3 ingredients and 2 of them are the same ingredient. So the integrator, like I said, forces us to have a low frequency phase of minus 90. Now each of the real poles are going to tug down at 45 degrees per decade, centered at 10 radians per second, but starting 1 decade below. So starting about here and ending about here, if I have two poles tugging at 45 degrees per decade down, that means that the combined slope is 90 degrees per decade down. So every decade I'm dropping 90 degrees, and I want to go through that point. There we go. Okay. So again, if you don't know any better, you might as well start with the straight line approximation and then smooth it out later if you need to. That's kind of my ethos here. I know that I'm going to need to talk about the 180-degree crossing, and so that's why I introduced the 3 dB correction, which turned into a 6 dB correction in the magnitude plot. Okay, so that's why I introduced the smoothing of this kink there. Okay, so here in blue, we have the magnitude of L when C equals 1. And in blue down here, we have the phase of L when C equals 1. Questions on these two graphs? So this is basically Unit 7 stuff, but I'm happy to help if people have questions. Okay, so now that we have the open loop Bodhi plot, both magnitude and phase, we can get around to actually answering the question, which was, is the system stable for the given controller? What do you think? I'd like you to tell me.
No.
Correct. Why?
The gain is too high, so the poles kind of go into the right half plane.
Good. So are you thinking in your mind, are you thinking of a root locus diagram?
Oh yeah, I'm thinking the root locus diagram.
That's great. That's, like I said, there are many ways to peel this orange. Also, what you can see is that the omega 180 frequency is exactly 10 radians per second. So this is omega 180, which means if we look upwards, we can see that the gain margin is positive or negative. What do you say?
Negative.
Correct. This is a negative gain margin because the magnitude plot is above 0 dBs. So here the gain margin is around about negative 4 dBs. Okay, and then we could also check the phase margin because the omega crossover is a hair above 10. And so we go down here and we see that, and then this is another kind of retention question. Is this a negative or a positive phase margin?
Negative.
It's also a negative phase margin. Good. So remember the phase margin is the amount of additional lag you can tolerate before crossing 180 at omega c. And this one we've already crossed omega 180. Or sorry, we've already crossed negative 180 degrees. So we cannot tolerate any additional lag. In fact, we have to remove lag is one way to look at this. So this is a phase margin of about negative 12 or 15 degrees.
So if a phase plot never actually gets to negative 180 or plus 180, is it always stable?
If the phase plot never gets to plus or minus 180, then the omega 180 is not defined, or you can think of it as being at either end of the Bodhi plot, which means that the gain margin is infinite. However, even if a phase plot doesn't cross minus 180, it can still have a finite phase margin. Which means that if you were to delay by more than that amount, you would have an unstable system, even though you couldn't change the gain to make it unstable. Did that answer your question?
Yeah.
Okay.
Would you just need a root locus then if it's in that kind of situation?
No, you could determine that from the Bodhi plot here. So maybe what are you thinking about, like the MCSL under proportional control? You have, so this is a quick aside. You've got your motor pole, you've got your integrator here, and if you draw the root locus, we have known for many weeks now that there's no way to increase the gain, theoretically, there's no way to increase the gain such that the poles go into the right half plane. Okay, so this would mean your gain margin was infinite. For any particular gain, you could increase the gain by an infinite amount and you would still be poles in the left half plane. So the Bode plot for this looks something like that. And the phase plot goes from minus 90 to minus 180. So this thing never actually touches minus 180, so there is no omega 180, but you could also think of that as omega 180 being at infinite radians per second. And how far is this distance between the magnitude plot and 0 dBs at infinite radians per second? Well, it's infinite. So this tells me that the gain margin is infinite without having known anything about the root locus diagram. The phase margin, however, is finite because there is a finite omega c, which means that there will be a finite distance between the phase plot and minus 180. So this phase margin is going to be finite. And you also could have told that from the root locus diagram, because if you had rotated the diagram by this amount, you would have been able to get the closed loop poles in the right half plane. So this is just saying that if you have an unmodeled delay in your system, you could still destabilize it.
So is it technically possible to destabilize any system by rotating it?
Yeah, in particular, if you use positive feedback, that's a great way to destabilize pretty much any system. And positive feedback is a delay by 180 degrees because it's multiplied by -1.
Okay.
Yeah, positive feedback, usually not a good idea unless you're trying to intentionally break something. Okay, so actually I want to save myself a little bit of room here. Let's get rid of that. Oops. So I think that we are ready to answer the question, the original question. No, the system is not stable if the proportional controller is set to 1. Follow-up question. And the reason for that is that both of the gain and phase margins are negative. Follow-up question is there a proportional controller that stabilizes the system? What do you think?
You'd probably want to lower the lower it so then a lower starting position. So
yeah, I mean, in particular, this gain margin tells us the answer. This thing says all you have to do is reduce the gain by 4 dBs and you will become marginally stable. So if you reduce the gain by anything more than 4 dBs, you will be closed loop stable. So follow-up is if C of S equals or is less than -4 dBs, is the system stable? And here the answer is yes. Because if we get a new color in here, let's try hot pink. If I were to change, let's get a concrete change here. So let's let C of S be 0.1. And for those of you following at home, this is a minus 20 dBs. Okay, so this is well below what we want. If C of S is equal to 0.1, it's still a proportional controller. It's just a attenuating proportional controller. What effect does this change have on the phase plot? I think nothing, because C of S is going from a positive number to a positive number, and so the phase plot won't change at all. If I change the proportional controller to 1/10 of its old value, then I get to move this blue curve, I get to shift it down by 20 dBs across the board. So there's 10 and 20, and there's 10 and 20. So now I'm connecting the dots here. So this is now magnitude of L when C equals 1/10. And here, the omega 180 hasn't changed, but the gain margin certainly has. So now the gain margin is approximately positive 16 dBs. So now we are well within the safe gain range. And I hope you'll also see that the omega crossover has moved to a lower frequency. And if I move the crossover frequency to a lower value, the phase plot is magically above negative 180. So now the phase margin in pink is huge. It's probably 50 degrees, 55 degrees positive. Okay, so by reducing the gain, the open loop gain, which was suggested to us by this negative gain margin, we are able to stabilize the system. Now that we have a stable system, I think it's reasonable to start talking about, well, how does this affect our steady state error performance? How does this affect our transient performance? But at the very least, we have something that's stable. Whereas before, it would not make sense to ask those questions about steady state and transients, because you could never get there because your system would always be blowing up left and right. Questions about this? So reducing the open loop gain is kind of the sledgehammer approach to this problem. Yep, it'll get the job done. No, it's not the best tool for this job, I don't think. So I feel like I'm going fast. I feel like you're not asking the questions that I would be asking if I was in your seat. I don't remember what questions I'd be asking if I was in your seat. Oh well. Reducing the open loop gain, sure, that will work. It works because it explicitly addresses the gain margin, but it also works because by shifting the magnitude curve literally down on the paper, we have to be moving the crossover frequency to the left, to lower frequencies. And phase plots, for most systems, will trend from upper left to lower right. Therefore, if you move the frequency of interest, the crossover frequency, to a lower frequency, the phase will tend to be a larger value, higher on the page, which means the phase margin will be positive, will tend to be positive. Okay, so if you're struggling for like some real world, I don't know if this is real world, counts as real world, but if you are presented with an open loop Bodhi plot and the magnitude and the phase are on top and bottom here, if those two graphs are physically close to each other on the paper, the system is more likely to be stable. If either the gain plot moves up or the phase plot moves down, then you're more likely to have negative margins. So anything you can do to move those plots like physically closer to each other on the page will tend to stabilize the system. And that's exactly for the reasons that I mentioned, that both of these plots tend to drop from upper left to lower right. And that means that if you were to move the magnitude plot down, then you are bettering your gain margin because the phase plot hasn't changed. So the omega 180 hasn't changed. So you are improving your gain margin, but you're also moving your crossover frequency left. So you're improving your phase margin. If I instead were to hold the magnitude plot fixed, so leave this blue curve the way it is, but somehow raise the phase curve, I think that would have the same effect. I wouldn't be changing the omega crossover because the blue curve wouldn't be moving, but I would be increasing the phase plot so that at any given crossover frequency, the phase would be a larger number, which means my phase margin is more likely to be positive. Also, by moving the phase plot up, I am moving the omega 180 to a higher frequency, which means that I'm more likely to be below the 0 dB line at that frequency in the magnitude plot. This is where I wish I did have the whiteboard so I could show you like, oh, if I move to the left, but I feel like this pen and ink is going to get kind of messy. Questions on what I just, on that diatribe? So I'm actually going somewhere with this. So if you believe that moving the phase plot up across the board would also help our margins, I'd also like you to believe that moving the phase plot up in only a small region would also help our margins. Okay, so follow along with this line of thought. If I were to move the whole phase plot up, so I don't know, arbitrarily, I'm not saying how I would do this, but if I were to able to move the phase plot up by 45 degrees across the board, now all of a sudden, the omega 180 frequency is up here, which means if we look up, we now have a, we now have a very healthy gain margin. If I go with the blue magnitude curve. So this is my new omega 180. And that means my new gain margin is much bigger than 0. So that's a smiley face. And what else has happened? Well, the omega crossover frequency hasn't changed. So I'm still looking here at orange. But now, if I look at that frequency, I get a healthy phase margin as well. Okay, so moving the phase plot up is just as good as moving the magnitude plot down in terms of stability margins. Now, how in the heck are we going to move the phase plot up? Well, if we could somehow time advance around the loop, that would be great. But that's a non-causal operation, right? If I want to move things into the future, that's impossible to do it for all frequencies.
Question, but why is it starting at negative 90 instead of 0 for the phase plot?
Because of the integrator.
Oh.
Yeah, so that's what I'm saying is increasing the phase plot by 45 degrees kind of across the board is impossible. But I wanted to show you that if you could do it, it would help. So I can't raise this by 45 degrees or by any amount of degrees across the board, and where across the board means for all frequencies. But I can increase the phase plot. I can bump the phase plot up over a small range of frequencies. Right? If I'm clever with my filter design, I can introduce a phase addition. We call it a phase lead in a small range of frequencies. And so my question to you is, if we return to the blue curves, where should the frequency lead or the phase addition be placed? Over what range of frequencies? What's the relevant range of frequencies that we would like to add phase to?
When it's at 0 dBs in the magnitude plot and 180 degrees in the phase plot?
Yeah, exactly. So this neighborhood, so this region is where all the action is, right? It's where all of our margins are being measured. And so if I could bump the phase plot in this region, but kind of leave it put in these regions, then I think I could do what I want to do. I would be improving my margins in the region that I want to improve them. And I wouldn't be breaking time-space continuum by saying I can tell the future around the loop. Okay, so that's the motivation for what's called a lead compensator. And I know you've seen this before because we've all had lab together, but this is lead compensation from the frequency perspective rather than from the root locus perspective. So that's the idea, is that an ideal lead compensator should add phase to a certain band, but not affect the magnitude. So let's see how that works. And a lead compensator looks exactly like this. A 0 and a pole. And pretty much the only thing you need to remember about lead compensation is in what order the 0 or the pole comes. So if I have the pole at a lower frequency than the 0, is that going to give me a phase lead or a phase lag? That might be a tough question to ask this early in the morning. So let's find out. So let's say this is 0 degrees, and I'm just going to do the phase plot for now. The pole should be, when you start 1 decade below, and it's going to drop by 90 degrees, so we get something like this. So here's the contribution of the pole, and then here is the contribution of the 0. So here's the phase of the 0, and here's the phase of the pole. And if I add these two green curves, am I going to get a phase dip or a phase hump?
Dip.
A phase dip. Okay, so this is not what we want. This is what's called a lag compensator. And the idea is that the pole drags the phase down. And if the pole drags the phase down before the 0 drags it up, you are net going to have a down and then an up. We don't want that. We want the exact opposite. So let's flip the script and put the 0 at a lower frequency than the pole. So if I put the 0 down here and the pole up here, then the exact opposite of what I just drew occurred. They both start at 0 degrees. The 0 goes up by 90 degrees. The pole goes down by 90 degrees. So here's plus 90, here's minus 90 degrees. And so the combined curve will be 0, 0, 0, and then it will start to follow the 0 up until it starts to feel the pull of the pole down. And then you tell me, what frequency or what phase is this curve going to stop at?
0.
Exactly. So the transfer function 0 has a plus 90 degree asymptote. The transfer function pole has a minus 90 degree asymptote. So the sum of those two says, this is probably too steep. There we go. If I add those two at high frequencies, then the limit of this phase plot is going to be 0 degrees. Okay, so this is the characteristic of an ideal phase lead compensator, right? It's adding, this is what's called the phase boost. And depending on where you put the 0 and where you put the pole, this boost can be placed at any frequency you like, right? If you literally can put the z and the p at any position on the frequency axis, then this maximum occur at any frequency. Now, what affects the size of this peak? We've talked about what affects the location. It's where the z and the p are on the frequency axis, but what affects the sizes? If I only want a little boost, what do I have to do to the z and the p?
Put them closer together.
Exactly. So the height of the peak is actually dictated by the delta, or the difference in frequencies of these two things. If they're far away, then the peak maxes out at 90 degrees. If they're close together, then the peak is only a little peak, and it's close to 0 degrees. And you can get a continuum of boosts depending on how close or how far apart the transfer function 0 and the transfer function pole are. Sounds good, right? Let's talk about magnitude, because everything I've said on this slide has to be talking about ideal compensators. So, and the ideal is if you could just have the phase benefits without the magnitude consequences. So let's talk about the magnitude consequences. If I were to take these two as I've drawn them, then the magnitude of the 0, let's say this is 0 dBs, The magnitude of the zero hangs out at 0 until it starts rising by 20 dBs per decade. And I'm going to compress the magnitude plot here. So here, this would go something like so. The pole does the same thing, but you flip it on its head, and then it rolls off at 20 dBs per decade. So if I combine these two, what's the high frequency magnitude going to be if I were to add these two green curves? Is it 0 dBs?
Yes.
Try again.
Oh, wait. Sorry, what was the question?
40 dB?
So this has a high frequency slope of plus 20. This has a high frequency slope of minus 20, which means the high frequency slope of their combined effort is going to be flat. But that doesn't mean, just because you have a flat slope, it doesn't mean you're at 0 dBs. So watch as we go along here. If I add 0 with 0, I get 0. If I add the poles 0 with the zero's upward slope, I get upward slope. And then if I add upward slope with downward slope, I get flat. Okay. So this is the consequence or the payment that is required to get this magical phase boost that we wanted down in the phase plot. You have to pay with it. You have to pay for it with high frequency gain. Which is explicitly not what we want, right? We'd like to be knocking the magnitude plot down and the phase plot up. This lead compensator will knock the phase plot up in the correct region of frequencies, but you have to pay for it by knocking the magnitude plot up at high frequencies as well. So how can we minimize the payment? How can we minimize this high frequency magnitude? If I want to move this high frequency level down, what do I have to do to the Z and the P?
You could just move them closer, right?
Exactly. So moving them closer would make this corner move to a lower frequency, or by the same token, move the 0 frequency up, and we could get something like, no, let's do pink again. We would get something like that, right? If this was the P prime, say. Okay, so it really is a transaction. If you want more phase boost, you have to pay for it with more high frequency gain. If you can afford a smaller phase boost, right? Because this boost was also proportional to P minus Z. And this distance here is also proportional to P minus Z. Or I guess technically it's P over Z, because we're talking about logs, but you get the idea. If you move P and Z closer together, you will get a smaller boost, but you also pay for it less. You will get a less smaller high frequency gain. Okay, so that is the motivation for why we have to strike a balance. We can't just make this thing way over there and this thing way over there, because eventually we would nullify the phase boost because we'd be amplifying our high frequency magnitudes, which would then move the crossover frequency higher, which would then move the phase margin negative. Okay, you got all that? Let's...
It stays high at the right side in the magnitude plot and doesn't go down again because of the pole.
Sorry, one more time?
How come it doesn't go back down again with the high frequencies because of the pole?
So if I add an upslope with a downslope,
Oh, I see. Never mind.
I get this behavior. Yeah, I'd have to add another downslope and another upslope if I wanted to get, so this and then that, if I wanted to get that kind of behavior in magnitude. And it's because the phase asymptotes to flat things, whereas the magnitude asymptotes to slopey things.
So if you need a bump in the phase in one spot and a dip in the phase in another spot, then you could do it?
Yeah, you could tolerate that. If you could tolerate, but remember, your dip in the phase shouldn't be such a big dip that you move your omega 180 up to that frequency.
Hmm.
Yeah. Okay, so let's try and address the same question, but with lead compensation. So this is a lead compensator whose pole is at 100 radians per second and whose 0 is at 10 radians per second. So what are we going to do here? We have got, well, okay, I'll start with just the plant. So I think that's a good place to start. Actually, I wonder if I could, yikes, do I even bother copying this? No, it's just too messy. Sorry, people. Okay, so we're going to say, so I get the frequencies right, 10 to the 1 is dead center, 10 to the 2, 10 to the 3, 10 to the 0. Okay, so we said this was 30 dBs, and so 20, 10, 0. This was our old magnitude plot. So this was 10, 20, 30, 40, 50. Okay, so this is our kind of uncompensated, or this is magnitude of P as a function of omega. And this was minus 270, minus 180, and minus 90. And so at 10 radians per second, the uncompensated phase passed through this point. So I'm just duplicating our work from 2 slides ago. This is the phase of P. Okay, so let's talk about the magnitude and phase of C, because if I can draw the Bode plot of C, it's cascaded with P, so I just get to add them. Okay, so C of S, if I write it in leading ones form, is 10 S over 10 plus 1 times 10 over S over 100 plus 1 times 100. So the 10 and the hundreds will cancel, and so I get that kind of pure zero and pole behavior. Okay, so the compensator 0 is at 10 radians per second. So here we'd have something that looks like starting at 1 decade below and going up by 45 degrees per decade. And the compensator pole is at 100, and so we get something like this. So the overall effect on the phase plot is, I'm still sloping down, right? Because this is a plus 45, whereas this is in blue a minus 90, but I get something effectively like this. And the high frequency phase actually isn't affected because this and this will eventually cancel each other out. So all I'm doing is I'm adding this little boost, this little phase bump in the region of interest, right? That's because this green curve is tugging the phase up a little bit, and then this green curve is then ushering the phase back down a little bit. So I change the slope here from something that's exactly minus 90 to something that's a little less than minus to something that's a little more than minus 90, and I end up at the same place that I left off, okay? So how do I pay for that? I pay for that up here with a 0 that takes off at 10 radians per second and goes up 20 dBs per decade, and a pole that does the opposite. So this means that in low frequencies, I'm following the same blue curve, and I get a little bit of cancellation here between the upslope of green and the downslope of blue. So maybe not, that's kind of exaggerating. Because here in blue, we're going down at minus 60, and here we're only getting tugged up at minus 40, or sorry, plus 20. So maybe we'll get something about like this. And we still have the same net number of poles versus zeros, so the same high frequency slope is going to be still minus 60. Okay, so this minus 20, and this eventually we get to minus 60 dBs per decade. Okay, so let's answer the question, was it all worth it? Well, I guess you're not really positioned to answer that, but can we answer the question, is the system stable with this lead compensator? And I think the answer is yes, because we've pushed our omega 180 up to here, which means we look up. And now we have a healthy gain margin. Gain margin is positive. And we look at the crossover frequency, which actually hasn't changed that much. And we now have a nice and healthy positive phase margin. Okay, so I'm not claiming that these are the most accurate plots in the world, but I am saying that this is one. I hope that you see this as a way to practically boost the phase in a kind of finite range of frequencies. And that's all we need, right? We only need this boost in this range of frequencies because that's where all the action is. That's where all the phase margin and gain margin measurements are. There's no reason to boost out here or boost down here. The only place that you need the boost is right where the action is. That's what I hope you take away from this. And again, the amount of boost could be increased if we separate the compensator pole from the compensator zero, but you pay for that with a bigger bump here as well. Okay. Questions?
So you would use a correction like this as opposed to any other correction, or well, why would you use this over, say, just like proportional correction?
Right. So we established that we could stabilize the system with a proportional controller with a small gain, or we could do it with this admittedly more complicated controller. And that's a good question about why you would pick one over the other. And the answer is, if I diminish the open loop gain in proportional control, I will eventually make the system sluggish. I will eventually get penalized in my transient metrics. Whereas here, I can actually improve my transient metrics while also stabilizing the system. So think about in the proportional control case, this is our open loop transfer function. So under proportional control, we'd get these guys coming together, that guy heading out that way. So if I reduce my gain by too much, well, I mean, anywhere I stabilize the system, I'm going to have slow closed loop poles. Do you see that? They're going to have to live in this kind of slow region. Whereas in the root locus example in the lab, we saw that the lead compensator actually had the added benefit of dragging the asymptotes out to the left. So what we can see here is that we would get, well, we actually put the zero right on top here. So we get this, and then we get, so this is 1, 2, 3, 4. So this is now 5. So we get a little bit of kind of this behavior, if that makes sense. So this is what I'm buying with my lead compensator. I'm able to get a sweet spot in the gain that puts my closed loop poles at a faster transient position, but also buys me stability. You could also see this from the bandwidth. Like if you were to calculate the closed loop bandwidth of this system versus the proportional controller, this system will actually improve your closed loop bandwidth, whereas the stable proportional controller will have pretty poor bandwidth performance. Okay, thanks everyone, and I will catch you later.